tree. And in Bitbucket, what that code does is it goes out and loads up every single commit in the repository, loads it up into memory, into an object. And then we wrap it in a list, massive list possibly, and then eventually we call length on it, and then we have the number of commits. And you might understand that that doesn't scale very well, because even though loading up a commit from disk doesn't involve looking up at the actual contents of the repository or building diffs, it only loads up the metadata for the commit. It does have to go to disk, and so if you have twice the number of commits, it will take twice as long. Until eventually, as you can see here, you reach a repository that is so big that it times out. Now you can tell from the rest of the stack trace that this is a Mercurial repository. And funnily enough, or ironically enough, I should say, in Mercurial, all the commits are sequentially numbered. And so to get to the total number of commits in a repository, all you need to do is look at the most recent commit and its number, and you're done. So there's really absolutely no reason why this would time out the way it does. As in, this is just really bad coding on our part. The fix, unfortunately, isn't as easy as I suggested, because, well, it would be for Mercurial, but we also support Git. And in Git, there is no such shortcut or easy way of getting to that number. In Git, if you want to count the total number of commits, you will have to count the total number of commits by loading them up. And so we're back to square one. Now, that wasn't the only problem in this API endpoint. It turned out like there were many things wrong. This is really old code. There's many other things wrong, and we've rewritten this thing. So there's a new version of the commits API, and it sidesteps this pagination problem by not using offsets for pagination, but instead, in the response, return a URL that points to the next page. And so, you can easily follow it along, and the last page obviously doesn't have a link, and so you know when you've reached the end. So we don't need to compute that number. And therefore, we could guarantee that this new API, like every request on that new API, regardless of the size of the repository or any of that, we could service those requests in constant time. And it's a very important observation, because we were able to look at this problem, solve it by, admittedly, building a completely new API, but solve it by ensuring that the new API returns in constant time. And so if only we just go up to our real-time Sentry dashboard, and for every error that pops up, we go in, we look at the stack traces, we understand what's wrong, and we just fix the problem by making sure that all that code from now on runs in constant time. Well, if everything runs in constant time, there is no more variance in execution time, and therefore there will be no more unexpected slow responses anywhere. Therefore, your new constant time becomes your new 100 percentile, and all your problems have been fixed. Simple, except in the real world, of course, things work differently, because in the real world, quite often you will see that when you sit down to fix one of these problems, you're faced with code that is hard to refactor. Maybe it's just bad code because there's not a lot of abstraction, and meaning that a change that you make here ripples out and requires a change over there. And now because you changed that, which should have been unrelated, that touches upon something else. And before you know it, your change ripples out through your code base, and it takes days or weeks to fix this. What's more, because you're changing the entire code base now, you have a ton of opportunities to break new things. And so even though technically you could fix it, it's not really feasible. It's also possible that the problem isn't really in your own code, but it's in some dependency that you use. And it may even be like a program that you shell out to that you can't really easily modify. Or it might be, the dependency might be written in a language that you don't really master well enough to fix it. And then there are sort of non-code reasons, sort of environmental issues that could have an effect on the runtime performance of your services. So on Bitbucket, we do a lot of caching, and we use memcached for it. So we rely very heavily on memcached. And unfortunately, we're not very smart. And when we use memcached, we don't version our cache keys. And that has a consequence that whenever we deploy a new version of our production code, we are forced to flush all of our caches. And if you flush all of your caches on a very busy site, you can imagine that that's going to lead to a brief but very, very violent spike in load. And if the load goes up on all of your servers, obviously, things are going to slow down, and you're going to run into all these new timeouts. Now we could fix the caching problem by not being stupid and just properly versioning our cache keys. But I'm raising it because there are many other sort of similar causes. So for instance, you might be running housekeeping jobs that are expensive on your servers occasionally, like maybe you're doing backups occasionally, or maybe you're pre-computing an index of some sort. All these things, have an influence on how your environment runs. And then there is the arguably the biggest or most difficult to anticipate, and that is user input, or unpredictable user input, basically. So in Bitbucket, the biggest problem perhaps is people that think that it's a good idea to push up 50 gigs of binary data in MP3s or whatever into a Git repo onto Bitbucket. Technically, you can do that, but it doesn't work very well. I advise against it. And it gets us into trouble, because now whenever we try to compute a diff for that, or even just access those files, we're going to time out, we're going to run into all kinds of problems, we're going to blow up in memory, and et cetera, et cetera. But it's also us trying to linkify content. So whenever we render some user-provided input, as in like a commit message, for instance, or the description on an issue on the issue tracker, or a comment somewhere, like whenever we render those things, we scan it and we look for patterns that we recognize. We look for things that look like commit hashes or other Bitbucket username accounts and other repos and stuff like that. And whenever we find those, we turn them into hyperlinks. So just basically to ease navigation. And the way that we do it, pretty simply, is by using regular expressions. So whenever we render a piece of text that a user typed, we run a whole bunch of regular expressions against it to come up with all these links. And regular expressions are terrible when it comes to predictable runtime, because the time it takes for a regular expression to apply to a piece of text is dependent on, well, the complexity of that regular expression, the size and the shape of the document that you run it against. Here's an example. This really seemingly innocuous regular expression, if you run it against that tiny document, it will run longer than this talk. And so there are tons of reasons why, just saying fix your code, make sure it runs in constant time, isn't going to help you. And so instead, like either you're faced with the decision to either drop this really cool functionality because you cannot guarantee that its runtime in 100% of the cases, or you'll need, I don't know, some other pragmatic way of handling it. And so we looked at the latter, right? So we weren't willing to drop any of this functionality, and so what we did instead was we went back to our alarm handler from earlier, and we turned it into a generic library that we call interrupting cow that can time box and interrupt arbitrary chunks of Python code. Here's an example. So here's a tiny program that has a busy loop, and it's wrapped in a 2-second timeout that will raise runtime error if the busy loop doesn't exit. Well, the busy loop doesn't exit, and so if you run it after 2 seconds, it will blow up with runtime error. Now, timeouts are reentrant, which means that you can nest them. So here what you see a 20-second outer timeout that raises one type of exception. And in there is a smaller inner timeout that raises a different type of exception. And then in there is the code that might be very expensive. Maybe it's quick most of the time, but sometimes it's going to be very expensive. And then what we do is we anticipate the inner exception. So we wrap it, and we catch that exception class. And so then when it does time out, we trigger that except clause, and we do something else instead. And hopefully that is cheaper. Okay, so the idea here is that you accept the fact that you're gonna run code that might be slow, but it will be fast most of the time. And so the one time that it is slow, you apply this and you do something else that is cheaper. It may not provide the same level of usefulness, but at least you're able to service a page. So let's see how we use this. So go back to the linkification problem. So we didn't want to drop that. So what we did instead was we used interrupting cow to turn it into the following. So what we do is whenever we need a pattern match a document, we only look for the very first occurrence of the pattern that we're looking for. And then we cut the document in two, like the first bit with the first match, we apply the match, and then the remaining of the document, we feed recursively back into ourselves, which will replace the next one and the next one. And then eventually, on the return, we concatenate all the strings, and we end up with the full document properly, but progressively linkified. And so here you see how it works. So at the bottom here, you see a timeout of 100 milliseconds. And in there, we call replace. We call replace with a document, which could be anything, a regular expression, in this case, something that looks like what we think might be a commit hash, and an action, which in this case turns it into a hyperlink. And then in replace, inside of replace, you can see that the first thing we do is we search for the first occurrence of that pattern, and then if we find one, we chop up the document in half, we apply it to that one thing that we found, and then we concatenate that with the recursive result of the remainder, right? And then on every level of the stack, because this is recursive, on every level of the stack, we anticipate the timeout, because it could happen anytime. And when it does occur, we ignore the timeout, but we seize any further recursion, right? So what we end up with is a document that is the original document, but part of it will be linkified, and the rest may not be linkified. And the good thing is that we can now guarantee 100 millisecond runtime. So no matter what we feed into this thing, no matter what kind of regular expressions we've got, we'll never ever spend more than 100 milliseconds on it. So either you get something that is completely linkified, maybe nothing is linkified, or something in between. So it's really pretty powerful, and we use this on Bitbucket all the time. Now Bitbucket is written as a Django app, and we use a lot of Django, and we also use the templating engine. And so what we wanted is a way to be able to declare timeouts and time scoping in the templating engine. And so we came up with a time limit Django templating tag that takes, you can see it in the middle, that takes 2 subfragments. And it will run the first fragment if there's enough time. If there's not enough time, it will run the other. And actually, I got to go back 2 steps because I got to point out that in the bottom example, you can see that the way that you can specify a timeout is either through a float literal, like the 20 second, for instance, but you can alternatively you can use a quota object, and a quota object is a way to declare an amount of time that you can then reuse in consecutive calls to timeout. And every call to timeout with that quota will only be able to use as much time that is left in the quota. And that comes in really handy if you use it in loops, such as here. So here, you've got a fragment that renders a list of commits. And for every commit, it renders a couple of properties, and one of the properties is diffstat. Now, the diffstat of a commit is the number of lines that have been changed in that commit. And in order to be able to count those, you'll need to produce the diff first. You got to do a full patch, which is very expensive, potentially, and then count the number of lines. And it's very expensive because a larger commit will take longer to compute a diff for. And there's really no upper bound in the size of a diff. So what we did was we wrapped the diffstat in a time limit. And we use a quota object with 1 second, which means that as we loop through this thing, we'll keep computing diffstats until we run out of 1 second. And then the remainder of, if there are any remaining commits in the list, they will just have diffstat not available. So again, we can guarantee that we'll never, no matter what kind of list we display, we'll never spend more than a second calculating diffstats. Now, I'm not advocating that you should start and wrap everything in timeouts and that this is somehow a silver bullet to performance engineering, because obviously it's not. It works best if you have a problem where it works fine most of the time, but not always. And in that small number of cases, you can think of a sort of a lower quality version of your result. Then it works really good. And if you choose to use it, you get some really nice, unique aspects. So one thing is that time boxing this way works really well with legacy code, right? So all these things that you can't really change because maybe the software that exhibits the problem isn't yours, you can't touch it, or maybe you can touch it, but it would be too expensive to change. All these things you can basically just apply timeouts to, and that will just work. The other thing is that really nice is that it provides sort of a pragmatic approach, or sort of a handle on the problem, regardless of the reason that something is slow. So if whether it's slow because of a busy loop, like CPU bound, or because of its I/O bounds, because you're waiting on external services, it really doesn't matter that interruption always works. And then there's the thing that it fits nicely with one of Python's philosophies. So one of Python's core philosophies is that it's easier to ask for forgiveness than permission. And what they mean by that is that you should take an optimistic approach to coding. So call the things that you want to do and write that code. Assume that it will work, and if it doesn't work, you catch the exception and you deal with it afterwards. And that is sort of in contrast to the more pessimistic philosophy of look before you leap, which characterizes some other programming languages, where you're encouraged to do all the checks up front and make sure that what you're about to do is going to work, and based on that, decide whether or not you're going to call it. Likewise, like using interrupt and cow or timeouts in general allow you to just assume that everything will work fine, and if it doesn't, then you have a failsafe. And then lastly, it adapts really nicely to server load. So when a machine is under load, like there comes a time where if you approach like 100% load of the machine, everything starts to execute more slowly because you've got to share the resources and you've got more work than you've got resources. And when that happens, your throughput slows down, and that typically compounds to the problem because there's more coming in that you can process, and so there's a buildup of these pending jobs or requests, and your stuff can fall over. Now the funny thing is that if you apply timeouts to put a hard cap, like a threshold, a hard cap on execution time, what happens is that regardless of the load, your throughput of requests per second doesn't go down. It's not affected because you've put an upper bound on it. It will never run for longer than 100 milliseconds, for instance, regardless of the load. So you sort of trade requests per second for a lower quality of the data that you output. But it also means that your machines don't fall over if you reach critical load. So then, to summarize, page render times depend on tons of runtime factors, right? So don't look at an average number. That average number is going to be low. You don't care about most of those fast requests. You care about the slow ones. You care about the slow ones because they get people in trouble. Those requests have a disproportionate impact on the usability of your site. And so to fix those, make sure that first of all the problem is visible. You know the problem exists. You know how big the problem is, and you know where the problem is by, as I said, making it visible first. And then go in and solve it. And don't just go ahead and wrap everything in timeouts or something like that. Do all the hard work first, right? So refactor bad code, and pre-compute indexes if you need to, paginate. Do all these things, and even remove functionality or say no to building new functionality that in your heart you can't really offer in a scalable way. That's hard, but do all of that. And then, however, if you do find yourself in a situation where you've got this really awesome functionality, you really don't want to drop it, but there's no way you can guarantee responsiveness in all cases, think of applying time boxing like this. Thank you. That's all I have.
Thank you very much.
Yeah, sure, if there's time for questions.
So have you looked into any other dimensions other than like clock time, like clock ticks? You're talking about servers being loaded up and resource shares being split. Have you had any usage for that internally where you would say like, your timer is now a share of the CPU, clock ticks, not seconds? Does that make sense?
You mean wall time versus prof time, basically?
Yeah, exactly.
So so the question is, there's a difference between what I'm doing here is basically just looking at wall time, like total time spent versus cycles spent on the CPU. The two things are not the same, right? If you've got a process that is I/O bound, you're not spending, the machine is idle basically, and so you're not wasting any cycles. So should you interrupt that? Well, it depends. Like in our particular case, this is about making web pages responsive. And so to the user, it doesn't really matter whether they're waiting on CPU cycles or on wall time or external services. And so we've never found a need to limit it to CPU cycles, essentially. But you could do so, right? So this is based on standard Unix alarm signals, and you can use those, or they allow you to watch for wall time or prof time, and so you can just change the library and use it that way. But yeah, we have never had a need for it.
Okay, thanks.
So I suppose you don't use any threads, right? How do you kill threads?
Right. So yeah, two questions. Do we use threads? No, we don't. Or rather, like we do use threading in some places, but not for the parallelization of our web servers. And so using signals as we do here and threading doesn't play nice, right? So using signals, you can use signals, but you can only signals predate threading in Unix, and you can only interrupt the main thread. And so this would not work for like the Gunnycorn with a multi-threaded worker, for instance. So for us, the problem doesn't really exist. Could you, the second part of the question, I guess, could you make this work with multi-threaded code? I think you could. Well, not with interrupting cow as it is now because it's signal-based. But if you spawn a background thread that knows that there is multiple threads executing, and you keep track of when a request started, et cetera, and then you go in and interrupt a thread, you got to think of a clean way of doing that. But if you could, well, then there's no reason why you couldn't make that work. But yeah, we don't do it.
Do you know where the name interrupting cow comes from? Because I think I know.
Well, where do you think it comes
It's a knock-knock joke.
What's that?
It's a knock-knock joke.
Yes, it is.
Okay.
Yep.
All right.
It was,
Do you want to start? Or?
it it's actually, so I'll give you the story. It came up. It was invented by a guy on my team, who the product manager actually, and he came up with the thing, and it just, I don't know, it had a ring to it, and so it stuck. But yeah, it's a knock-knock joke.
Yeah. Well, I think we should do the knock-knock joke. So, knock-knock.
Who's there?
Interrupting cow.
Oh.
Moo.
Any other questions? I have a question. So when you run code that So my question is, when you run code that can be timed out or interrupted based on how long it runs, that can produce kind of unpredictable thing, or can kind of do unpredictable things based on how long the code runs. So like say something in your else statement or whatever, like does some other thing that might have a bug in it, and you want to test those things. So like how would you write unit tests, or some kind of, how would you try to ensure that, your code works the way that it does, or that you expect it to?
Well, so what is the question exactly? As in, how do you go about unit testing things like this?
Yes, or how might you do that using interrupting cow?
I'm having trouble really understanding what you want to know. As in, if you want to test whether your code works without any of this timeout stuff kicking in, you can just turn it on.
Okay, so like in the case that like it kicks in, you want to test like that, it still works, and in the case
Right, so you
that
wanna-
it tests
right,
that
exactly.
it doesn't
So you
kick
wanna
in,
have a-
you want to check that
Gotcha.
it works.
So you want a reliable way of making sure that whenever my test runs, it always interrupts it at one point in the code. Is that what you mean?
Yeah, perhaps. Like, say if like your interrupting cow will, interrupt after 30 seconds or whatever, or after a couple seconds, you want to say like, okay, write a test, or say that, send an interrupt that says that executes the code the handling code in the timeout.
Right. Yep. Short answer, I don't know.
Okay.
As in, so I don't have a solution for that. So yeah, couldn't tell you.
What do you guys do? Would you like have unit tests, or do you just kind of not really worry about that stuff?
The truth is that we have no tests for making sure in an automated way that the interruption produces the expected result. So.
But you have some tests that you just don't worry about it, or you just
in the tests that we do have, we never trigger those timeouts because the time is very high, like 30 seconds. We don't have tests that.
I see.
Or we shouldn't have tests that run that long.
All right. Thanks.
I can quickly answer that. You can use mock, and exception so you could actually test the behavior.
Well, it'd be tricky, right? Depends on what you wanna interrupt. So for instance, if you want to interrupt the execution of a regular expression, you're outside of your code, right? So now you have to stub out or, yeah, exactly, but.
Object that's like being called, so like if you're calling the regular expression object, you could patch that out and it like calls side effect on an object which just raises that exception immediately. So like it would be complicated if you wanted to introduce a delay, but that's probably a bad idea. But otherwise you could identify whatever the best object is for your situation. It's definitely more complicated with things like regular expressions, but you can usually come up with side effects.
Yep.
But I would agree that it's probably not worth testing.
Well, maybe it's worth testing, but it can be very hard to test. Yeah.
Well, I mean, if like it goes over 100 milliseconds and your page like was 500 errors, then you might want to test that. But
I guess the other way that you can test it is to only test the code that you're supposed to run and test the exceptional case when it runs over a certain time amount, right? And just pretend that interrupting cow will always work, right? That's not really working.
right. I mean, the issue is that like the parts that you interrupt or whatever, like is code that you actually do.
Right.
Any other questions? Okay, we're good. Yeah, we're out of time. So thanks everybody, and thank you for your talk.
You're welcome.